This slideshow is all about faults. As an example of a fault, here we have in this slide this a spectacular exposure of the Wasatch Fault Scarp in Utah. As you'll find out soon, this is an example of a normal fault, and this particular normal fault poses a pretty severe risk to the people who live in the valley where Salt Lake City is located. Now, the primary classification of faults is based on whether the motion of slip is in the direction of the strike or the dip. And this means that if you're not really familiar with the concepts of strike and dip, you need to go back and watch that video again until you're absolutely certain you understand the difference between strike and dip. Remember, just in this little picture here, the strike is a direction which represents a line that's the intersection of the horizontal surface and a dipping plane, and it's a line that's always horizontal. It has a direction we could describe as like north, east, south, or west. Whereas the dip is the angle of that plane, the angle that plane makes from the horizontal. And the angle is measured with increasing values as the plane gets steeper and steeper and steeper. So a dip of 0, remember, means horizontal, and a dip of 90 degrees means perfectly vertical. But again, if you're not familiar with the concepts of strike and dip, you'll be confused in the sections that follow. So make sure you go back and review that. In a strike slip fault, the motion is along the strike. And in a strike slip fault, then you're going to have generally horizontal motions with a fault plane that's close to vertical. In a dip slip fault, the motion is in the direction of the dip, and that means it's going to have some vertical component, right? It's either up or down the dip of the fault plane. So let's look in a little more detail about strike slip faults. Remember, these are faults in which the slip motion is parallel to the strike. The fault plane is nearly vertical. And these kinds of faults are caused by shear stresses which sort of attempt to smear the earth. One arrow going in one direction, one arrow going in the other. We can classify strike slip faults as either being right lateral or left lateral. And the rule here, this is what's shown as a right lateral fault here. The rule is that you stand on one side of the fault, look across the fault, and describe what you're seeing. So if you do that here, you can see that the other side appears to be moving to your right. So this is a right lateral strike slip fault. A left lateral strike slip fault looks like this. So the same rule applies. If you stand on one side and describe what you're seeing happening on the other side, in a left lateral strike slip fault, the other side will appear to be moving to your left. And if you want to play with this, you can see that it really doesn't matter what side of the fault you're on. The definitions will still work if you do it exactly as I just described. So here's a little practice here. Here's a kind of classic example of a strike slip fault. Can you determine whether this is a right lateral or left lateral strike slip fault? I'll give you a second. Correct. It is a right lateral strike slip fault. I've drawn my little arrows, and you can see that as I stand on the side closest to me and look and describe what happened in the other side, it's moving to the right. So that's a right lateral strike slip fault. How about this one here? What you're looking at is the land and you're looking out of an airplane, so you can actually see the wing is sort of in the picture here. But you can see a river here, and the river is making a sharp right turn. And the reason for that sharp right turn in the river is because it's been displaced by movement along a strike slip fault, which is again a right lateral strike slip fault. Okay, turning now to dip slip faults. They're a little bit more complicated because there are actually two different kinds of dip slip faults, and they're very different. It's really important to keep them straight. And the difference is based on the direction, the relative movement of the two blocks on opposite sides of the fault. And so what we need to know is have some way of identifying the two blocks in a dip slip fault. And to do that, we use a concept called the hanging wall and the foot wall, which is actually an old mining term. So what would happen is that miners often saw that mineralization occurred along faults. Fluids would circulate along the faults and create ore minerals. And so faults were very commonly places where they dug their mines. And if they dug their mine down the fault plane, then they would find that there'd be a gap there, and that the part above them where they would hang their lantern would be called the hanging wall, where the part on the where they have their feet on the bottom would be called the footwall. So the hanging wall then is the part, if you sort of imagine a vertical man or woman standing right on the fault plane, the hanging wall will be the part where his or her head is, and the footwall will be the part where his or her feet are. So here's an actual mine, okay? You can actually see that they've dug out this in pursuit of ore, and you can actually see then clearly that the fault is dipping into the screen, and the wall above is the hanging wall, and where they're standing on the footwall. So can you figure out this one here? You see, in most cases, we don't actually have a mine. So in most cases, the hanging wall and the footwall are pressed tightly against each other. And the idea, again, is imagine sort of a vertical person standing right on the fault. Put the belly button, if you will, right on the fault. Head will be on the hanging wall, foot will be on the footwall. So imagine this guy here, just lift him up a little bit so that his belly button's right on the fault plane. And his head will therefore be on the hanging wall, and his foot will be on the footwall. And as long as you can keep that straight, we can then describe the differences between the reverse faults and the normal faults, which are the two kinds of dip slip faults that you need to understand. So here we have it. Here are the two types of dip slip faults. Again, they're really different, and it's important that you don't confuse them. They are called normal faults and reverse faults. They're equally common. I don't know why they call it normal, but they do. A normal fault, if you look carefully, is one in which the hanging wall moves down relative to the footwall. So you can sort of see it in the animation below. The hanging wall is the block on the right, right? And it's moving down the ramp of the fault. In a reverse fault, it's the opposite. The hanging wall, the block on the right in this case, is moving up the footwall. It's being pushed up the ramp of the fault. That's a reverse fault. Normal faults are caused by extensional forces, pulling apart forces. And you can imagine sort of the reaction if you pull this rock apart, the rock tries to stretch, and as it does that, it sort of has one block, it breaks, and then as one block slides down the fault plane, it actually widens to accommodate the extension. A reverse fault is exactly the opposite. A reverse fault occurs in response to compression. So as we compress rocks, we cause them to break, and then we literally shove one rock up and over, and as we shove that rock up and over, we're actually compressing the rocks and making them more compact. So reverse faults form due to compression, and normal faults form due to extension. There's one other special kind of fault you should know, and that's called a thrust fault. And a thrust fault is really nothing more than a reverse fault, except it's usually a giant fault with an enormous scale, many kilometers usually of motion, and it's got a very low angle fault plane. A lot of times these things are so big it's kind of even hard to see them until someone points them out to you. For example, in this picture shows a classic example of a thrust fault, and you might see that reddish rock, right, is different than the green rock beneath it, and that's because it has literally been shoved up and over to the left along a very low angle fault ramp. This is a classic example of a thrust fault. In some cases, thrust faults can even have ramps that are nearly horizontal. A good example of this is found in Glacier National Park, which is a park I would recommend visiting someday because it's just spectacular and beautiful. But most of the rocks of Glacier National Park actually didn't form there. They formed somewhere else, and they were shoved up basically horizontally from the west, many tens, perhaps hundreds of kilometers. They were shoved along a very low angle fault ramp, the one shown here in red. So all of that material that I've circled here in orange was shoved up and over along that very low angle thrust fault ramp. That's kind of the typical thing we see in a thrust fault, a very low angle fault ramp and a gigantic fault, one that moves enormous amounts of rock, enormous distances. Most reverse faults tend to be much smaller in scale. There's one other thing that you should be aware of, and that is that normal faults often occur where the earth is being stretched, or they do occur where the earth is being stretched. And in response to that stretching or extension, the earth breaks into lots of little blocks and you get normal faults. Well, these normal faults often occur in sets as shown in this diagram. And if you look carefully, you'll see that every one of them is a normal fault, right? The hanging wall is moving down with respect to the footwall. And as a result, it creates sort of low-lying areas separated by up sort of mountains. So we have mountains and valleys, mountains and valleys. The valleys are called grabens after the German word graben for grave, and the uplifted areas are called horsts. So this kind of terrain produced by extension and a whole bunch of parallel normal faults is called horst and graben terrain. A really good example of horst and graben terrain is found in the Basin and Range province of Nevada, New Mexico, and California, shown on this picture here. So all of those mountain ranges here, each of those mountains here, all of this topography, I should say, is formed by extension. The entire earth here is being pulled apart. And in response to that extension, lots and lots of normal faults have formed, producing grabens and basins. So if we look at the actual topography, we see that all of these sort of northeast, southwest trending mountain ranges consist of the uplifted portion of the horsts, and all of the intervening valleys, which are full of sediment, correspond to the grabens. So this is a perfect example of sort of horst and graben terrain caused by extension. Here's a picture of what the basin and range looks like. Again, what you're looking at are those mountains running sort of across the screen here are the horsts, and the intervening valleys are the grabens. All of this is produced by normal faulting.